All right, let's get started. Welcome back. I hope some people have already started with the exercises. Anyone? All right, very good. Good to see. I can recommend starting early. It takes a bit of time to set the whole thing up. We know it's not, Visual Studio is not necessarily everybody's favorite, so I can recommend it to start early. Also, realistically, our tutors only have a limited amount of time right before the deadline. So if you have questions, it usually does pay off to ask well in advance. Let's jump right in. So last time we left off with the Taylor series. First sight, a pretty classic, old topic. Who remembers what the idea was, or why? What's the point? Why look at Taylor series? Let me pull it up just for completeness. Although I can admit, right, out of the equation itself, you don't get too much. So I hope you remember. So important thing is we have the step size typically called h. We have some old value xn, and we want to get the new one. At position n plus 1, we're assuming we're just counting n from 0 up to some number. We're at some n, doesn't matter which, we want to get to the next, h apart. It's an infinite series, and good to keep in mind, there is an equal sign. It's identical. What we get out here and here is the same. Mathematically, you can show exactly the same. But what's the point? Yes. Yes, very good. Keyword, numerical approximations. Maybe, do you have an idea how do we get from this to an approximation? Exactly, yes. Thanks. So, to recap for the recording also, so we want to, this is an infinite series. The equal sign only holds if it's infinitely long. That's a problem. It's not feasible in the computer. So, going towards a numerical approximation, what we will do in practice a lot is we cut this off. Was in a way very intuitive, already indicated here, we can't even write it up. And if we can show that we can get away by just computing a few of these terms, right, then we basically have something, and then, also as mentioned before, then it's not an equal sign. So we get back to that today a lot. It's not the same anymore. And I already showed pictures like this one. So this is a typical problem, right? That we encounter here. Don't want to restart the whole idea here, but right, we have some reference function that we want to approximate. We're not exact anymore. We will drift. We'll go away from the solution. And the question is a bit, how far? How can you control it? What do we need to do to get back or to prevent this from completely blowing up and going away from the solution we'd like to have? And the most basic method that we already have just kind of slipped in, and that you also probably heard from other methods, other lectures, as a starting point for these integration methods is Euler's method, which is really great because it's so simple. So this is, in a way, even if you want to go very complex, always a starting point. And if you look around, in a way, it's actually used in a surprising amount of settings, despite its simplicity, or right, maybe because it's actually so attractive, because it's so simple. So we have the same picture as before, our step size h, and then we basically do the simplest thing possible from Taylor series. We just take the very first term, right? You could leave even that one out, but then we'd only be left with a constant value that just keeps repeating the old one. There's no point, right? But we take at least one term, the absolute minimum. We get this one with the first derivative. Keep in mind we have this ODE set up, so our derivative is given by this f here. Right? This gives us as repeated up there, the derivative, so the tangent, and then we have the step size h here. So we're just taking, knowing the tangent, we're making a step by h in this direction. So this tells us the steepness of the line you want to have, and then we just go forward by h. The important thing here now is, I'll keep on repeating myself just to make sure, is that this y1 here that we're getting out is not, if you want to write it out, I think I do have it on the slide somewhere, right, this is not equal to y of x0 plus h. We don't have y. This is what we cannot compute, but instead we're getting an approximation from our y0. So yeah, it's actually exactly written down here. These are not the same. So it's all, just to recap the notation, the subscripts, the y here, so now mean we have these not accurate versions of our function of the thing we're interested in, and these y1 or yn or y whatever are not exact. But okay, now we're at the same position. Now we have this y1. Now we can go to y2 and so on. All right, so here it's the general form again for step n. Of course, also yn is not equal to n times that step size. Holds for any n, of course. Yes, there's a question. What exactly is the function? Can you remember what last week? What are we trying to compute? So the question is, what is the y? Yeah, right? Or that is the question. So, sorry. The question is what x0 and y0 are, not what the y is. So, talking about the basics, it's a good starting point. It's important that we're on the same page for the notation. So maybe for any, what is this y we're interested in? If you think about our application, right, we have these mass spring systems. What could be y? Yes. Right, so there were already a few candidates here. You mentioned position, velocity, and acceleration. That's a good direction. Exactly. Any forces also played to give it away. Basically, accelerations and forces are kind of equal and typically something we compute. So in practice, right, this will be either position or velocity. Actually, those two are the ones we're interested in, right? Also for the exercise, if you looked at it, the forces we basically get from Hooke's law, but we're interested in how does that influence the velocity? How does velocity influence position? So later on we have two of them. Now we're neglecting one. I mentioned already last time, if we have a higher order ODE, we can split it up into first order ODEs, right? So in a way, we can stick to this viewpoint of just looking at one. Later on, we just have to do it multiple times. And now your question was the x0, y0. So what that is specifically, or what was the question?
Yeah, I saw like the x0, y0 is a function. And I was like, if it is a function, then what it does?
It does exactly this. Computes the derivative. So if this is, if we're interested in the position here, right, then that would be the velocity. Or if we're interested in velocity, f would be the acceleration. It's a derivative. And the important thing now is we need to start somewhere, right? We need to set up our simulation. This is also in the exercise typically you're given, right? You have the 2 points, this position, this is where we start, they're addressed. You need to know where to start evaluating this. exactly to start this whole process, right? We need to evaluate the new value here, the y1. We need to know the y. And in order to evaluate f, our derivative, we need to know where we are at x. So typically x is easier. Later on, that's the time. So we just need to say, well, the state is at time 0 or time 1000. It shouldn't matter, actually. But we need to know my particle starts at position 10. Otherwise, right, I cannot compute this. So h is given. This is, we choose 1/2 or 1/10 or so. But in order to evaluate Euler's step and to evaluate f, we need these parameters. Also, I didn't mention last time, for higher order ODEs, we typically need a whole set of them, right? So second order, we also need to have initial conditions for the velocity, say, for the first derivative in order to evaluate the second one. Yep.
Why is practice positional velocity?
Mm-hmm.
Always time or basically always time?
In our setting and in our application later on, exactly. Yeah. So this is most often used for time integration to compute steps over time. It's also how we'll use it. But I want to connect here to the general literature, which doesn't care about time, just about some dimension. And you can actually, right, it is really abstract. You can actually compute other integrals with it. It's a very basic concept, but we'll typically use it in terms of x being time. And right, for now, for the next few slides, feel free to just think about the y being the position where we're at. I mean, literal, I have a graph in the one. Okay. Just pull up the graph. All right, so I'll stick to the ODE notation here with x and y. And you can imagine this being time and this being our position. Right? So imagine you have a 1D space, a line, and then something moving along this 1D line over time. And right, typically the thick line here, that's a reference. So here we'd like to get a particle that at time 0, or whatever reference time we give here, starts exactly here. Whatever unit it is, then has this trajectory. So I think it's good to think about this. Right, then Euler method. Okay. Picture, we define 0 to be our starting point to be at this spot. But right, I hope it's intuitive. Time, in a way, is this somewhat special dimension in physics. Typically, it does not matter whether we say this is time 1000 or a million or 0. The physics should be the same. So typically, time is a bit special, but it's this x-axis we're looking at. And now we can start with this Euler's method. So, right, this f that we need to evaluate, and that can for now be anything, but again, think ahead of Hooke's law or something along those lines, gives us a tangent. Steepness in that point, and if we know the black line, you could somehow read it off, or we could have other ways, but typically we don't have easy access to the black line, but we just have this function f that tells us the steepness, right? So basically, how steep is this line in this point? So even in general, again, just a tiny amount to a different place could give us a completely different answer. It's a point-wise estimate of the tangent in exactly that spot. We have the mathematical property of a derivative, only in that point. And then we just make a step along that tangent. So here now, right, beware the notation. This is x1. Here's a dashed line. There's already a dot here. This is a dot we'd like to have, but this is the one we don't get, or that we typically also often don't know. Instead, what we're getting is something just shooting along the tangent, along the orange line, and this is now our y1. Right, so also conceptually, the x's are easy, right? So we just step this time forward. We know we want to get an answer at exactly time x1, and in a way, right, that is exact, because we know this doesn't depend on anything. It's just we make the step forward to x. So x1 is exact. That's the true answer. But the y1 up here, as already indicated, this is the quantity that is typically difficult to get and that we don't get exactly. So already you can see it here, right? We already have a bit of a gap here. Because of exactly this property, we're looking at the tangent. This true curve is curved. It changes, the derivative changes in this case. It's probably growing a bit more positive as we go right, and we are just using the information we have at time x0. But then we keep on going here. So I have a few more steps here. Sorry, here. Great. This one I wanted to show. You can imagine doing this an arbitrary amount of time, but here it's shown for 2. I hope the picture is clear. Here, in a way, for our ODE viewpoint, for time integration viewpoint, it doesn't matter that we're not exactly on the black spot, right? We can be anywhere along this line. We can evaluate our f. It can be very wrong. So far, we haven't dealt with that too much, but we just get another tangent, and then we're making another step with this, and we just keep on going. So you can imagine this is like, so the nice thing, as mentioned before, that's now the great thing about this Taylor series is we don't need that much. We don't need the whole y, but we only need something telling us the derivative. Then we need some initial condition, and then we can go along this trajectory, right? So it's kind of like finding your way along, climbing along this black trajectory, and in a way we're making steps, or we're like reaching towards the next position that can be anywhere here, right? So we don't, unlike a real workout or so, where you need to hit a certain handle, we can just stop anywhere in our space here and make another step anywhere else. And of course, later on, we want this to be as close as possible. But for now, the concept just works moving in this space, in this 2D space for this example. Also looking ahead, so what will actually later on be crucial is the size you're using for these steps, right? So here, this is the h, and I hope you can already imagine a bit from this picture. If h is actually very small, we make a tiny step, and then the next derivative that we're getting will actually be pretty close, and we might stick closer to the desired black curve, whereas if we make a very big step, right, you could, for now, h is not given or constrained. We could make a step that's any size. This arrow might grow a lot. So this h is actually a crucial parameter to kind of keep the arrow down a bit. Yeah, so in a way, Euler's method is great, the starting point. You can derive it in terms of a Taylor series and this truncation, but it's really as simple as it gets. We have a derivative, we're making a step along that derivative to find the next point. So the concept, I hope, is clear. Yes, there's a question.
The function for the derivative, why can't we just integrate it?
So the question was, we have this f, the function for the derivative. Why can't we integrate it? How would you integrate it?
There are some functions which are kind of impossible to integrate. I mean, like everything which is kind of simple would be integratable.
So I guess with integratable, you mean this analytic way, right? We have the equation written out. At a high school way, we could try to figure out the integral and then get an analytic expression for this integral. No, unfortunately, the bad news is it's really not. In the general case, it's not even, typically not even possible to just write out one equation that tells you for one variable, this is the integral. I'll come back to that in a moment. They will be coupled. And for now, in the general case, also, it might be really difficult to do this. So kind of, no, we're actually assuming the derivative we can get. But this integral we cannot set up. I'll give some more examples in a moment. Right, it sounds a bit artificial, but also if you think ahead, what we're interested in, or from Hooke's law, the pictures, we have some forces. And from the forces, we'd like to know where are things, the position. So we actually need to have two derivatives. So one integration step is not enough. We need a double integral typically. And the functions can be really complex. We're dealing with a very simple law with this linear forces from Hooke's law. But if you have a few 10 points and then on the order of 10, maybe 100 springs, and then damping terms and so on, the functions will be actually very complex. And we need to integrate twice. So in practice, it's very difficult, and actually in many cases not even possible to just write out one equation because they depend on each other. So it's really it's a really fundamental problem. And also nice thing in a way here is that we don't need to make any more assumptions. We need to have this f, the derivative, but also it's enough to actually have a higher order derivative. Acceleration from forces is enough. Could be even the third one or fourth one in other applications. Right? In physics, I think there's not even good intuition behind that, but theoretically it could be even higher order, and then we could find our way back to the very first fundamental quantity by doing this multiple times and kind of skipping this analytic integration step. So what's important to keep in mind, I think I mentioned a couple of times by now, this is now first order because we only have a first order term. Right? We're leaving away everything that's higher, second or higher order in the Taylor expansion here. Always question is, can we do better? And the obvious answer is, putting it on a slide like this, yes, we can. It's actually not too complicated. We have the Taylor series already. We can basically now just start adding more of these terms. So that will keep us busy for a bit because there are a couple of different ways to do it. And it's interesting also to look at the differences in terms of answers that you get out from doing this. So in a way, I think most intuitive way to get started here is what's called by now known as Hoyne's method. And the idea is that we basically first do an Euler step, and then we can see this as a prediction that tells us a bit more than what we had in the original state. And then from that new estimate, we're just repeating. We're doing another evaluation. And then we have 2. That's a bit better than 1. And from those 2, we can do a combined update. So the idea is here, just like before, standard Euler step, but instead of just saying, well, this what's now called y tilde here is the end result, we're doing another evaluation of our f. Right, so this is our derivative, Euler step, and now we're doing it again, 2. And we're saying, sorry, this is a new one. Right, this is the same. We're reusing it, so we don't want to recompute it. This might be expensive, but we can just reuse it, right? You can store it. This is a new one at the y dash now. So we're doing the evaluation of the derivative a second time, and then we're just averaging. Seems primitive, but you can actually show this is mathematically reasonable and a good approximation for the second order terms to say, well, we take now one whole step by h, just basically applying a factor of 1/2 to both of these f's. Right, so we have both of them weighted by 1/2. And this is now, as one can show, already a second order method. So this is now essentially taking the next term of the Taylor series into account. How does this work? It's also nice to draw it out one time, starting as before by some step h. And now, contrast to before, we're not just continuing from that point, but now we're going in and re-evaluating our f. As mentioned before, we can evaluate f, it's a function. We can evaluate it anywhere we like. Basically, can be very wrong, but we can just plug whatever state we have in terms of x and y into our f. And this is now shown here with a green line. It's also, that's why these additional curves are here to highlight what f does in the background, basically, apart from our reference trajectory. And now we're getting this steeper second derivative at this point. Again, this is probably a different f to the one you would get here at exactly that spot, but we don't have that. Can't get it. In this setting, basically, pretty much impossible to really be on that black spot. But now we have one f, another f, both are tangents, and now we can do this weighted step. So now we go back to the beginning. So we start from x0 and then make one combined step with this averaged, half-weighted derivatives that we have from the previous steps. And in this picture, and we can show in general, being second order, this is really now fundamentally better. So this gets us closer in terms of this distance here to the true trajectory that we'd like to get. It's also a lot more costly, basically, right? Potentially, we haven't defined this f yet, but this could take work and computational resources to evaluate, and now we need to do it twice. Right, but this is the basic idea of Hoynes' method. It's also called a predictor-corrector method because basically you can see this first step, the first Euler step, as a prediction step, right? We're kind of looking into the future a bit, but we're not using it, correcting our estimate by doing another f evaluation, and then with this correction, we're doing the final step towards the end answer. Another variant that also is second order, we get to that in a moment. At first sight, it might not be obvious why, right? Do we need, or why would you want another version of this? But Hoynes' method is not the only way to get a second order method. And this midpoint method is actually also a very widely, not so wild, but widely used method that you can find in quite a few applications. So that's why it's worth mentioning it explicitly here. It's part of this Runge-Kutta family, which we'll come to in a moment, but I think midpoint is actually a pretty midpoint, or basically RK2 are names you'll both find for this method. So the idea here is slightly different. Instead of basically doing this prediction step and then correcting, we're saying, well, right, we're going somewhere, we know this is wrong, so instead, let's take a partial step. So the big difference, and hence the name, midpoint, we're going to the middle. Mathematically, it doesn't make sense, too much sense, to just go at arbitrary positions. So we're just making a step. That's the main difference now of size 1/2. Remember, h is our full step, and now we're doing half a step. So this brings us in the middle of our x0 and x1, the midpoint, and the y tilde of midpoint method accordingly is the middle point between the two evaluation steps. And then you can show that instead of this averaging step, it's actually also second order accurate if we just do one more evaluation of this f at this midpoint and make a full step forward with the tangent we're getting at that spot. So we're starting somewhere. Instead of going all the way, we go halfway, find our derivative there, and with this tangent, we're now making the full step to the endpoint. Thinking ahead to the questions, for this f, we need both x and y. So the x, in a way, is easy to compute, right? We know exactly what x should be and will be. But for this midpoint to get a good answer or the correct answer for f, we actually need this y here, this y tilde, because this is actually the xy position that we get from our scheme in this case. So this is x and y. With that, we can evaluate f, make a step size of full range, h in this case, and with that, this again now looks like almost like an Euler step, right? So we start at y0, h times the derivative. Main difference is that it's computed at this midpoint, and this is actually second order. So, oh yeah, I don't have this on the with the schematic, but we look at this in a moment for these more generic Runge-Kutta integrators. Again, I think these are important to mention. Might sound a bit weird at first. Runge-Kutta, well, they invented it, came up with it mathematically. Forgot when, but it's pretty old, very classic scheme. And this is now a whole family of methods. So that Euler, Hoyne, midpoint are all these specific first or second order methods, and the Runge-Kutta is any order. So also came later, but it's a very generic formulation to construct an integrator of any order. You can choose which order you want to have. It can be 100 if you want or so. What's in practice, however, very popular is the fourth order Runge-Kutta method. It sounds a bit arbitrary, but turned out that this is actually a good compromise between computation and accuracy. And this is also called some texts or circles mother of all integrators, because this really fundamental method that gives you pretty good accuracy, and hence is also used in quite a few applications that want to do something more accurate. So if you basically have a chance, or it's important to go away from Euler, get something better, then Runge-Kutta is a popular integrator. Yeah, so I don't want to go through the whole family, this whole setup, but just introduce the fourth order one. I think from it you'll already get the picture a bit how this is set up. It's in a way quite nice and has a certain symmetry and behavior, but I think it does make it's not necessary actually here to really deal with the generic case of any order. So we'll only look at the fourth order version here. And now we're kind of sticking to this midpoint approach of doing multiple steps forward and then reusing those to make a final step. This is actually how all of these, all of the integrators you get from Runge-Kutta work. So, as always, we start with our Euler step. So we first compute what's now called a k. This will just be our derivative, an evaluation of f. Initially, we don't have anything else apart from x0, y0. This we kind of need to start here. Now, like before, midpoint is also a Runge-Kutta method. We're doing, in a way, the same idea is now written in a bit more compressed way. If you think back, the x we can easily increase by our h h over 2. And here in the back, you now basically see what was on the previous slide, the y tilde. This is now basically doing a step forward in terms of this y from 0 by 1/2 with that tangent here. That's written a bit more compressed because we need more of those. This gives us a k2. Now we're taking this further. We get a k3, and turns out for the Runge-Kutta method, actually what you now do is we're going back to x0, and we're doing another halfway step with this k2. And see, this k2 now is in a way an even better approximator of the real direction. We're kind of redoing that step with a new value. And then finally, we are doing another full step with this k3, but it's again not the final version, but this is just another k, the fourth one. And then with all of these 4 k values, right, all of them are derivatives, same quantity, we can just weight those. This is now in a way a bit similar to the Hoyne's method, and from the 4 directions that we got out here, do one combined update and go forward. And here now we have a factor of 1/6 for these. As you'll see, we actually have a weighting of the other terms by basically 1, 2, 2, 1. We do want to get a normal kind of tangent, or this could be a velocity or something that is correct in our setting out again, right? So we basically normalize this by multiplying it with 1/6 here in the front. So the quantities still match, and we have a step that's on the same order as the same magnitude as the other steps. Now just computed from all of these 4 directions. And this now you can show actually represents a method that takes the first 4 terms of the Ortelli series into account. So this is now again quite a big step forward in terms of accuracy.
How much better is that than doing like smaller?
The question was, is it any better, or how much better is it than just doing 4 Euler steps? Very good question. I'll come back to that in a moment, but I actually do have a slide for that because it's a very good thought. But for now, I want to give a few more details of the Runge-Kutta method, and then we can look at the differences of, right? Well, also, we had now first order, second order, now this is fourth order, right? Does it make a difference, or why would we do this? So far, I haven't really discussed this. Let me first illustrate Runge-Kutta here. We'll do quite some back and forth now, right? So, but it's, I think, still good to draw it out once. So starting at our x0, make our Euler step towards the half. We get the first tangent, do another step with that to the midpoint. We get another one, the third one, do a full one, right? So this was this refinement step, second, third, and then we're doing a full step to this point x1 here. There we collect another derivative, the k4, and then we combine them and make a final step to the endpoint. And this example now is actually not made up. This is from a, this does make sense mathematically. Or we can now see a bit, I mean, the previous second order methods were fairly close already, but this now gets even closer. It's hard to draw a proper gap here. It's pretty close to the actual black curve now, as I hope you can see on the slide as well. But yeah, it's definitely a lot more effort than the other methods. We now had 4 of these evaluations of our f. Haven't said what it is, but this could be costly. So it's a good question to keep in mind. Well, does this really pay off? First, some more notes about Runge-Kutta methods. Yeah, we could build a 100th order integrator here if we'd be interested. The concept would be very similar to kind of evaluate this interval we're looking at 100 times then with different specific positions that are computed from the Runge-Kutta algorithm and then combining them. But yeah, at some point, because we still need to make this step, it actually does pay off less and less. So this fourth order was found to be a good compromise. If you run the Runge-Kutta algorithm, construct the second order method, then we actually exactly get this midpoint method. It was part of the fourth order method already, and right, it's still a nice kind of generic way to look at these methods. And if you now think back about the different versions that we had, well, Euler was first order, required 1 evaluation of this derivative of the f. Hoyne and midpoint, which I don't have on the slide here, but right, midpoint likewise here, required 2 evaluations of f. So twice the effort, but gave second order, which I so far just mentioned, but it's actually looking ahead, the order, if you think back to the Taylor series, right, we had our expansion of terms, we had our y0 and then the terms. The order really here comes from the h, right? So we basically had h1 and then h squared, h cubed, and so on. And these factors here, this is more a direct multiplication. And so here we have an exponent. This is really an order, cubed or so. Whereas this factor of 2, this is basically 2 times something. So order actually means an exponent, typically. When we talk about the order of a method, we're dealing with this and not a factor. So that's an important distinction. And does actually also make a difference, as I'll show in a moment. But right, a good question here. Now I have it on slide. Why don't we just do, if the effort is to run this f4 times for Runge-Kutta 4, why don't we just do 4 Euler steps? Let's try it out. For this demonstration, I do have the simplest possible ODE that you can write up in this form. So our ODE now is this one. So the derivative is derivative of y, which we typically use here, is y itself. Then we're setting, as before, we actually need to start somewhere. We need to know an x and y. So these are our initial positions. This is our starting point. The x is somewhat arbitrary, but we're starting with y at 1. And the equation here looks very simple. Any intuition here? What could we be looking at here in terms of function if we say y dash equal to y? Yes, an e function, right? The e to the x, right? Exactly, is the function where the derivative is the function itself, which is basically this condition. So basically trying to compute an e function here in a more complicated and costly manner. But this is great to know, because knowing exactly what comes out, we can now go in and do what we normally can't. We can check if we get a yn, right, some approximation. We can check what was the real y at that position. So we can really quantify and compute the error we're making over the course of the steps. So later on in UML string systems, if you try the exercise, for most cases, if you go away from simple harmonic oscillators, you actually won't be able to do this. But given this formulation and our ODE here, we can now, for example, compute an Euler step. And if you now think about our formulation from before, or Taylor series in general, we basically have something with these different terms. And here we normally need to add all the derivatives. Well, this is our ODE. The ODE means our derivative is the function or the approximation we have, the y. That means we're basically always making a step, changing that y, and reusing that y and adding it on top, right? So in the first step, basically our derivative would be 1, because this is our ODE. Derivative is equal to whatever our current solution of y is, right? So it's actually very simple to code up. We keep on adding the current value to some accumulator. All right. To make it slightly more interesting, what we can do here is we'll actually try to get to a certain x. So we're think about this graph we always had, right? We're starting at x0 here, and then we'll try to make a certain step towards the target x. That's this interval here, right? So 0 to some x. And we'll basically now look at different ways of subdividing this interval into steps. Namely, we'll call that n. So we'll have n steps to reach this target x, and then we'll see, right, how much error are we making, because by then we'll actually have some y. Right, we have our approximation yn at the n step, and our reference is e to the x. We know that. So we rely on basically having a good answer here from a computer as some underlying library, but trust me, they're pretty good. They'll definitely be much better than what we're computing with our approximators. So we'll have a reference answer that we evaluated this x, then we can check how far apart are we by taking the magnitude. So how far, we don't care if we're above or below, but just the distance to that true answer. Right. And I do have that as a small program that I want to show off in a moment. Right. We'll do that in a moment. So what then is actually another interesting variant that we can do is, well, we can, as before, we can compute our integration. We can run our algorithms for this target x with our n steps. Then we get this distance, the error, right, that we're making towards the target. And then an interesting question that we can also try out is basically, we have an error, but how many of these sub-steps, how large does this n need to be in order to get a certain accuracy. And this is what I'll show in a moment. Out how many of these steps do we actually need for a certain method in order to get below 10 to the minus 6, for example. So get a pretty accurate answer out of it. Right. And this is something that we can just try out in a moment. But timing-wise, I think this is a good time for a break. And then afterwards, I'll show the demo here. So see you in 5 minutes. I'll start a timer real quick. All right, let's continue. So, question that just came up here, floating point accuracy. I've completely ignored for now, especially for this example now, of course. So far, we were mostly on the slides, right? Mathematical, assuming we don't have errors. For what I'll show now on the computer, we, of course, will have numerical errors on top, but what we're assuming for this chapter, I'll get back to it, but for now, is that all these calculations we're doing are far away from floating point accuracy, right? We don't want to mix those two. That would be a separate topic, basically. All right, but so here I have my, yeah, you can see it, my great example program, right? So this is now exactly the implementation of what we just had on the slides. So I'll stick to double precision here, exactly because I want to make sure that floating point precision does not get in the way of what we're doing here. So floating point for doubles is typically 10 to the minus 15 or something. So we're at 10 to the minus 6, pretty far apart. But here we're setting up a few variables, the x and y. This was our starting point from before here in line 8, x equal to 0, y equal to 1. The endpoint for x I haven't specified, but this will be 2 in our example. And here now we're just making 20 steps as a starting point. So n equal to 20, and our h correspondingly is the length in x divided by the number of steps we're doing. So this will be 2 divided by 20, 1/10. But here for the general case, it's just written out. Yeah, and then we're making n Euler steps. So it's written in the, well, here's a loop over n, and it's written in the generic form here in line 14. We're not labeling the y, right? On the slides we had 1, y 0, 1, 2, and so on. In a way here we'll just have y. This is our accumulator. So we'll just overwrite the old value. We're actually not reusing anything here. So this is the yn, if you want. And the Euler step here is written out in terms of y plus h times our derivative. And now how do we implement the derivative at this position? It's this function f here. You can already see it at the top. And this is now pretty easy. It's actually stupid to write it out this way, but just to stick to our formulas at the very top, line 4, you can see f just returns y. That's our ODE, right? Derivative is y. So, but to stick to the more familiar expressions in the loop here, I've written it out in this way. And then we're computing the new x, and this code now just prints x and y. And then at the very end, this is also a bit interesting. Right here, we're basically computing the absolute between the reference and our approximation, the y20 in this case, we would probably call it on the slides. And the reference is just the exponential function at 2 from a standard math library. All right, so this we can run. The code we can we put on Moodle later on if you want to play with this, but it's you can also feel free to code this up yourself. It's really pretty simple. If we run this, it's not too impressive, but now we're getting our 20 steps here printed out, intervals of 0.1, and here the second line, those values are our approximations of the exponential function along the way, and the end result is now printed down here, 6.7, whereas e to e squared basically should be this 7.38 and so on. So the error we're making is actually around 2/3. Yeah, okay, so far so good. This is pretty obvious. Let's make it a bit more interesting as mentioned before. So now let's try to get this error below 10 to the minus 6, which is pretty small. And let's check what n do we need, how many steps do we need to get below these 10 to the minus 6. And those are the next examples I now have. Oh. Basically still the same program. There's just now a do while loop here that does this until we hit the 10 to the minus 6 for the error. So here we now compute some error. In line 23, that's reused here. This keeps on going. And it just increases the n at the very top here in line 12 for the next iteration. So we'll actually, we're starting at 0, and then we go higher and higher until we are below 10 to the minus 6. So any estimates? How many Euler steps do you think we need? We had around 2/3 before for the error. How many divisions will we need to get below 10 to the minus 6? I also couldn't have said, but typically you don't have a good intuition. Well, let's try it out. That's what the program is for. So it might actually be slowed down by the printing here a lot now, but as you can see, now it's running. This is our error. We're definitely now way better than before. Before we had 2/3. Now we're at 10 to the 4. But if you observe a bit in the beginning, it went down pretty quickly in the first stages, and now it's not changing much. We're still at 10 to the minus 4. Now we're at 1. You can see it counting in the 6th digit here. We're already at 82,000 steps. So now we're actually making more than 80,000 steps to go from 0 to 2 in our interval. And it's still counting. So if I would let this run, it would actually take a while. But probably it would be a lot slower without the printing. Probably this is now limited by the printing. And if you think about it, it's actually pretty stupid because knowing that it increases so slowly, we should make much larger steps, right? So there's a version that just runs in large steps of 10,000. And now we're getting somewhere, still running, but now we are approaching the 10 to the minus 6 boundary. I should have still increased this a bit more. But yeah, so in the end, it's more than 1 million steps. I think I have the exact number on the slide. So I hope you can imagine. So we're not right now, we're at, oh, this is 8 million already, right? So this is more than 10 million steps or so. So a lot of steps. Basic point here is if we want to get to this very low accuracy, then Euler's method does really badly. So this an insane number of steps in a way. We already discussed, we have alternatives, right? We don't need to be limited to Euler. Let's look at Hoyne's method. Also to just quickly show the implementation. Here's our y tilde from before, making a step by h. And then we're making another step here. So here are the two f's. I hope you can see right, with the mouse pointer. In this case, this is the second step and this is the first one. And then weighting them by 1/2. And now from more than 10 million or so before, this is the second order. And this is now pretty fast. This is not increasing by larger steps. Here we only need 3,100 steps. So this is a lot faster, right? So it's really running the whole thing here. This is a good indicator of this right, exponential nature that we're looking at here. First order or something higher order, right? It's not just a factor of 2. This is a factor of, I don't have it, well, more than 1,000 that we're getting from the second order method. Okay, so we had Hoyne here. What does midpoint do in contrast to this? In this framework, it's simple to code this up, right? We're just doing 1/2 step here, and then evaluating our derivative at this midpoint. It looks a bit different. How well does this do? Exactly the same number of steps. So this doesn't need to be the way. So as mentioned before, floating point accuracies could distort this, but this program is so simple that the floating point errors don't play a role here. So second order really means in this example we need exactly the same number of steps. But also, again, this factor should be similar. It should be a large step no matter what second order method you take. Now, of course, lastly, let's look at fourth order Runge-Kutta. This is now slightly more involved. So here we have all these different k's. This block in the middle from line 18 to 21 is evaluating f 4 times now at these different midpoints, and here directly written in terms of the Euler steps, right? So here we are updating the y always, but it's really exactly what we had on the slides basically. And then, right, this is the weighting, so 1/6 times this weighted sum of the derivatives. And any guesses how many steps will Runge-Kutta 4 now need? Yes, there's a 10. All right. Let's try. Almost 38, too optimistic. But yeah, it's still almost a factor of 100 now for the. Well, this is now 2 orders more, right? Euler to Hoyne or so was first to second order. Now we went from second to 4th order. But this is now really, in a way, very, very small runtime. And this is a bit where the numbers came from. Of course, when trying this out, I had to choose numbers that make sense for Runge-Kutta, and here we now at least need a bit more. But for Runge-Kutta, this is now almost too easy. So Runge-Kutta can really solve this very, very efficiently and in very few steps. Yes?
So the computing power scales linearly, but the accuracy is like constantly getting better. At what point do we expect to use 5th order or 6th order equations?
So the question of the statement was, right, so the big difference here is that the order is something that scales with the exponent, that changes potentially very strongly, whereas the runtime, so here the variation time of this Runge-Kutta method was, well, so for runtime, a bit of a reason why I don't discuss this here in too much detail is the function, this f we had, is super simple, just as a return y, right? So there's essentially no effort here. Or maybe the optimizer of the compiler will even leave that out. So it's almost no cost. But if the f would be more costly, and in practice, right, thinking ahead to mass spring systems, that's where the work is done. Then these 4th order Runge-Kutta methods are roughly 4 times as costly. But unfortunately, as with many of these theoretical considerations, we're talking about exponents and these factors, the cost of the f and the actual implementation is a bit hidden in this viewpoint. And unfortunately, it depends on what you really have. It depends on your case, how well it's optimized, whether this will pay off or not. So I'll have a few more examples in this chapter and the next one. So we come back to this. It's in a way a pretty fundamental topic. But unfortunately, I cannot say when you need to compute this and that, then use 4th order or otherwise use 5th order. It then depends on other considerations like hardware. But one of the reasons why I'm going through all of these examples here is that it does make a big difference. That's a bit the main point here. So it's good to be aware of it. And then if you have a case where it might pay off, it's actually worth considering whether you can save runtime with these methods. But we also actually get to examples where it does not make sense to use these nicer higher order methods. But for my spring systems, it does, and will make a big difference. Right, so a bit the main message is here, as we increase the step size, we're really fundamentally changing the answers we're getting, and here's actually now a difference between 1 and 1/4. It's not just a factor of 4, as you can see with the blue line, but really something more to 1/4 to some power squared or cubed, or it's basically amplifying the change. Also mathematically, it's good to keep in mind this is with respect to the time step. So when changing this h time step or the step in the integrator we're making, this is when the differences will kick in. This is potentially a quite well studied and interesting topic. Just to hint at it a bit, you can, again, we've kind of looked at these algorithms in more detail now, but you can bring it back to the Taylor series and then look at how the error and these terms that are neglected influence the solutions, how that evolves, and what statements you can make about it. And it turns out that the errors typically develop in terms of the highest order terms of what you left out, which, if you think about it a bit, is actually not too unintuitive, right? We have different terms here, and assuming that the h is somewhat small, we're taking different exponents here, h squared, h cubed, and so on. So if h is at something close to 0, this will grow tiny, and it will be smaller and smaller. So the largest part of this left out terms, truncated terms that we looked at here were actually the square terms, so the second derivatives with the h squared. And if those do something bad, give you a crazy value, a large derivative is indicated here a bit, right? If we have a not so simple function that has some sharp points and we're directly hitting the spot, then the derivative, the steep line we're seeing here, this then bounds the answer you're getting. So whenever you have a function, even if there's a tiny part with a large derivative, mathematically that can cause trouble, or basically indicate that the solution you're getting is inaccurate. So the mathematical considerations typically look at the boundedness of derivatives, or the next higher order derivatives in these truncations. And from that you can make some mathematical statements. But I think the main idea is that it depends on the highest order terms, and if you're interested in specific applications, again, it depends a bit on what your function, the y dash, also does. There you can actually find additional analysis of how the errors develop. So the one of the important points here is what we already discussed, but just for also people who want to look this up, it's here on the slides. So we typically have linear increase in calculations for the higher order methods, say n times more for an nth order method, and something exponential typically in the time step, h to the n for the increase in error, increase in accuracy, decrease in error. A practical advantage that is worth taking out is typically that means if the error per time step goes down, if you think about it the other way around, you can make larger time steps without getting a big error. So that's also for real-time applications or something where you have limited resources, an attractive viewpoint. So if you have a higher order method, not so much computational performance, you can now take a bigger step forward. And typically the error depends on the nth derivative in these approximations. Yeah, also for real-time applications, it's worth a moment to think about what this correctness means. So if we go back to this classic example of trying to compute the trajectory for a ball, we might want to give it a kick, and we know it has a certain trajectory, ballistic motion, or so it can be even very simple. And an extreme example could be, well, we have a player shooting a ball, should reach a goal. It's either, if it's inside, we have a score of 1, and if it's outside, here, it's just 0. We don't get anything. So we are mapping this continuous space of behavior to a binary decision, 1 point or no point. Yes, there's a question. Yeah. So the question was, I said, if we know the error is going to be small, we can take a larger time step, but how do we know that the error is going to be small, basically? So what I meant there was, you know that for Euler's method, for example, you will typically get errors on a certain range, but then if you set a typical time step for your application, say your mass spring system that you want to show, and you go to second order method, then you actually get a lower error. So you can rely on basically from first order to second order for your specific application mass spring system with a typical time step to get a certain reduction of errors. So it's a choice of method, going to higher order methods, and if you then would go to, say, Runge-Kutta 4, it would be even lower. And then you could actually, unfortunately, again, there's no analytic equation to tell you, well, if you go from first to second order, you can increase the time step by factor C. In practice, it depends on the application. Again, you probably have to try out how much you can increase the time step before things blow up. But it's actually something good to try in the exercise. That will be very obvious with the mass spring systems. If you run it with Euler and then with some higher order methods, you should see a big difference in terms of behavior. So it's a good thing to try out. But yeah, basically from switching the method, you can rely on having a more accurate answer. Right, and for this case, it can actually make a big difference in terms of the score, right? So we can have a correct answer, and our numerical solution might just differ by a small bit, but maybe bounce off or slightly go beyond the post, and suddenly we're switching in terms of score from 1 to 0. So for the game, this is a huge difference, right? For the numerical integration, it was just maybe a small bit where it's off, but a huge influence on the game. On the other hand, it sounds drastic, right? It's basically, it could be the choice between winning and losing, but probably in reality, for a game at least, this would not matter too much, because even the green line doesn't look too bad, right? Visually, probably many humans would not be able, especially if there's some action and so on, distinguish between these trajectories. Whereas if the ball would turn around in midair and go back or so, that would just violate all our assumptions and be obviously wrong, right? This would be bad. So this is something we need to avoid. But for these smaller differences, even if they have a big impact on the game, potentially, they're probably both fine. But it's a bit part of this whole discussion, and also something, unfortunately, that we need to get back to quite a bit. A lot of the decisions here are based on an application. So I'll try to give you the basics and basically know which parameters to change or what the options are. But then if you have a specific application and implementation, you probably need to be careful and choose the right one. That with these integrators, actually interesting nonetheless, you actually find options for that in many engines, for example. You have Euler or higher order methods or Runge-Kutta, order of some Runge-Kutta scheme. Also, this also comes up in UIs quite a bit, even if you don't implement it yourself, but this is a very common parameter. Yeah, so much for this discussion about accuracy and considerations. What I also want to explain today is we've looked at basically this, in a way, more direct Taylor series viewpoint of adding terms and getting errors down this way. There are other ways to improve the approximations. That's what I want to sketch out a bit here. In the context of the mass string systems, those are less relevant, but again, I think it's important to point this out. So one alternative is what you could call state-based methods. And the idea is a bit this classical runtime, memory runtime consideration. So we increase the accuracy by basically evaluating this f function, our derivative function, more often. You can instead save more memory versus runtime to compute a better update. And that's what these methods do. So the idea here is typically put to practice for higher order ODEs. So for this example, I actually need to go back to a second order one. So here we have some of this position and velocity. It's not so nice, or as far as I know, there's no good example to show this with a like example like the one with the E function. But nonetheless, I think the idea is pretty clear. Instead of evaluating this f more times, we're now storing history. So basically storing more data points. If you think back about all of the methods I showed before, and also the implementation of this E function example, it doesn't store any history. It's just one state at the current time, basically, at the current x. And instead now, there are methods that might save one or more n previous points, and from these reconstruct the shape of these functions that we're interested in. And this is exactly what, for example, this velocity valet scheme does. So the first order term here is first of the direct zeros order y values are not so interesting. This is a standard second order Taylor series here with the first and second terms. But where it gets more interesting is now this velocity integration, the integration of the derivatives. And here, what velocity valet now does is to use two values of y, and I show that what you need here is both the previous second derivative for step n and the new one that was just computed up here from n+1. And right, the new value of the first derivative is now updated with the second one averaged. Again, this is just a starting point. You could potentially bring even more terms in here by sampling back and forth. But you can see it a bit as an approximation, right? So we have some function here. Right, so this is something we need to calculate, and the other one is something you would store from a previous step. The idea here is a bit that if we have a graph, right, and some function, instead of just looking at the derivative at a single point, doing a tangent, basically saving an additional point somewhere. Okay. Try to draw it here. So from 2 steps, right? So you get 2 tangents, but you construct some, maybe a line through both points to get a better direction, or you could even think about doing some small polynomial and multiple points. So basically you're just using multiple data points, in this case from history, instead of from evaluation, to get a better answer for the main function. So this is one alternative, basically consuming memory, keeping a history. Another one is so-called implicit integration, which is also an important keyword to mention. And so up here now, the implicit is the important term, because what we've looked at so far is what we would call explicit. So we're having some state, typically at this nth step, we want to get to n+1. There might be even a bit of history, but we're just taking these and moving forward. And with implicit integration now, what we're instead doing is we have a state at time, right, at some time or position x for our nth step. And the idea is that the derivative now, this f that we're evaluating, we're not taking from the current one, but from this future location. The motivation here is a bit that for certain applications, the derivative here in the future could be better than the one we are taking at the current step. Now, what you're hopefully now wondering already is, well, how do we get this? Isn't this where we want to go? Right? On our graph, this was typically the next location that we don't yet have. Well, it's at first just a mathematical concept, right? You can write this equation out for whatever n, or right, you can do mathematical operations on it, and we can write this out for n+1, and in a way worry about the rest later. So what you would do here is actually literally that. You write it out for the next time step, and then we're in one of these cases where you can just easily say, well, now the new value is something based on the old one. But now we have a lot of equations that typically depend on each other and say, well, right, the velocity at n+1 is some expression and depends on other points and quantities at n+1. The velocity of the next point, again, is some expression that depends on all kinds of things from n+1. But mathematically, this is, in a way, just a matrix if you set it up correctly. So you get some relationships between different quantities. All of them you don't know, but you can write it out. Right? You now have a whole set of equations that depend on each other. Previously, we basically just had one equation. We had something we could write out, right? Y n+1 is something based on time n. Just compute it, then we get the new answer. This doesn't work anymore. Suddenly we have equations, potentially many of them, that all depend on these new values. But, well, also I'm sure all of you know, if we have a system of equation, we can still try to mathematically resolve it and find answers that satisfy all of these equations at once. That doesn't stop us typically from computing a solution. And the way this is done, I have a bit more details in a moment, is that we now look at all these relationships between the different quantities at this time n+1, and yeah, collect them as factors. A matrix, in a way, just collects factors from different terms, right? If we have a big matrix and we compute it with some vector, then basically we have some line here that contains a bunch of different factors, might be some zeros and 1, 2, 3, whatever, different factors that get multiplied with some incoming vector. But in a way, a matrix, we can think of it as a collection of vectors applied to an incoming collection of factors applied to an incoming vector. And this is a viewpoint that we're taking here. So we're collecting from a physical system how these different quantities at time n+1 are related. And then on a very high level, you can basically write it out as some equation, some big matrix A times this new state, y. It's a new time step equal to old stuff, some vector. This is what we can pre-compute and what we previously had, the B. And then you kind of just invert A. It's also something you probably know from school, right? If we have a matrix, we can invert under certain conditions the matrix and then compute the solution, the yn+1, by computing the inverse of A and multiplying it, bring it to the other side, right? Basically dividing, multiplying it with that B. We get back to that. I know it's a bit abstract, but this is in a way an interesting own topic. But that's the main idea. So we basically, for our physics, we collect these different coefficients, put them in a matrix, then invert the matrix, and from that we get the new answer. And I hope from the description already you now get the impression that this is quite different from the previous way, where you just applied our Runge-Kutta scheme and then got the answer. Now we have to set up the matrix and invert it, and computing that inverse here is actually also potentially computationally costly. So these methods really work a bit differently than before, but they have some nice properties. So at this point, I think it does make sense to briefly bring back the mass spring systems in a bit more detail. So what would happen here is we basically would get some big matrix that we multiply with a vector, and this here just written as a y for some current state. And now all the specific values here don't matter too much, and this actually quite quickly grows large. This is something for the computer, not so nice to write out. Nonetheless, if you imagine our y just having some values a, b, c that maybe belong to 3 mass points connected with springs up here, then if we think about it in 1D for now, in 2D actually you would just have 2 numbers here for each of those, wouldn't change the picture much. But if you think about it in 1D, then this matrix it basically gets multiplied, right? So here we would go A, B, and C from the top. So this encodes for the output of A how it depends on B and C especially. So typically there's some influence on itself, but for a point A, right, we need to know the influence of B and C onto that point. In practice, that means evaluating Hooke's law for exactly these positions. Say, what forces would we get out for the state of our system? And this is basically a factor for acceleration and change of velocity for these points. And this is something that would go into these 2 coefficients here. So here it's written as the influence of B onto A, the influence of C onto A. And then we would multiply this with the state, and you could think about writing out Hooke's law in this matrix form such that if we now put in a vector of all the states, it would just pick out the ones that are connected to A and give us a new answer for that point A. And then we can keep on doing that for all the points, right? So it could be many more points. Here it's just 3, but we go mass point by mass point and collect the influence. So here in the next line, we would have the influence onto B from C and A in our example. And then we have the influence of A onto C and B onto C. And here they're kind of all depending on each other. But again, right, if we had more points, the matrix would grow. It's basically quadratic in the number of points or values we have. And then you would most likely also see parts here, these quadrants that are 0. Right? So the diagonal will not be, but some of these might be just 0 when there's no spring. If there's a spring, that means there's a connection. And the actual coefficients in that quadrant of your matrix, in that part here, would actually now depend on Hooke's law. It's basically you're evaluating Hooke's law and calculating it for this one time step and putting this all into a bit matrix. And then all the parts that depend on the previous time step, those would go into the right-hand side vector. Then this whole matrix you need to invert with a -1 and bring to the other side to get the desired new state here. Right, so very different way of approaching this, and actually not super popular for mass spring systems, which is why we are sticking to these explicit methods, but we'll get back to these implicit integration methods for different problems later on, so it's good to mention here. And for now, the big takeaway is basically there are different ways of approaching it. We're dealing with explicit, but there is this implicit viewpoint. The important difference is that we evaluate the quantities of derivatives at this future time, which typically gives us this linear system of equations. It actually only works if things are linear. Yes, there's a question. Very good question. So the question was, the matrix grows if we have more points. Exactly. It's actually quadratic in the number of points. We had some, n is not such a good counter here. Let's call it m. You have m points. It's m by m. And then your dimension, 2D, 3D, would come on top of 1D. So for 10 mass points in 2D, it would be 20 by 20. And the springs now come in as entries. Those would be fill your 2 by 2 blocks or 3 by 3 blocks in your matrix. So if you had everything with everything connected, this would be a full matrix. But if you only had, right, again, 10 springs in here, then it's actually a symmetric matrix. Then above and beyond the diagonal, you'd have 10 blocks being filled. So if you now set up this matrix and one time bring it to the other side, that's a full step, like one complete midpoint step or so. So this does treat your whole system. You can actually also think of or evaluate these explicit methods, where it's depending on time n in this way, but it's just a lot less intuitive, and typically storing this or organizing this matrix is also work. So you can think of the explicit methods and basically just computing some other matrix A times yn, giving you n plus 1. But usually it's not such a good viewpoint to consider it that way, because you really only need it if it's implicit, if you need to invert the matrix. So bringing this A to the other side, that's in a way the important step for implicit methods, which is non-trivial. Quite some work, and this you don't need for the explicit methods. But so one, maybe to come to the intuition, why would you do this, right? So one very nice property is mathematically these implicit methods really have a fundamentally different behavior, namely that they're damping. So the explicit methods, which we looked at before, they just use some time, then go forward. The implicit methods look into the future. Mathematically, that's possible, right? In reality, that would be dubious, to say the least. But mathematically, you can say, well, I want to go forward with that value here that I don't yet have, that's in a future point in time. And you can actually mathematically approximate it, typically not fully accurately, but you can get a pretty good answer. And this now has the opposite effect of undershooting. So whereas the explicit methods go, if you have a curve like this, over, right, so here we have this main line that curves upwards. The explicit methods now stay below and go over. The implicit methods do the opposite and stay inside. They undershoot. And in some cases, this is actually desirable. So I had this example with the circle before, right? Where we want to go in a circle, and the other one had this behavior of spiraling out and exploding, With these implicit methods now, you get the opposite behavior, that it spirals into 0. 0 might also not be the most obvious nice answer, but the nice thing is it's actually stable. It does not explode, but goes to 0. And this simple fact, in a way, is actually interesting for many real-world applications, because you can show they're actually unconditionally stable, meaning you can make a time step that's as large as you want. You will still get an answer that does not explode. It basically just will not move or do nothing. It will go to 0 if done right. But usually that's better than something that produces crazy values. So that's in a way the big advantage of these implicit methods. They're pretty expensive, to be honest, but they don't explode. Yes? Yeah.
But like, it would be nice if the game was great, right?
Exactly. Exactly. It's actually very interesting for real-time applications where you might have a delay and suddenly a big step, and then you can be sure this won't explode. The disadvantage is that for this inversion step of this matrix, it's actually a priori typically not clear how much work that is. So for normal explicit Euler methods, you can really count the number of floating point operations to get to the answer. For this one, even especially for tough states, probably you will need more work also. So there are some considerations, but you're right. That's also why I'm bringing it up actually for, I think I have it on the slides. For real-time systems, this is a very attractive scheme because you can be sure it doesn't explode. Right. In practice, you actually do need other solvers, linear solvers, they're called, like the CG method that we also come back to later on. Right, we need to make sure it's linear. This is a point we've only hinted at a bit, but if you have really a nonlinear system, then things typically do become more complicated, but hence something like Hooke's law, that actually is a linear physical law, is nice, and a very good choice. And yeah, the disadvantage could be that, well, it's this damping, it's essentially damping that you get from these implicit methods can look boring, but at least it does not blow up. Although, right, you actually need to make sure your whole algorithm, everything is part of this implicit integration step. If there's just one sub-step that is not part of it, then that could again cause a blow up. So it's actually also, it can be a bit tricky to set up in reality. And actually, for games, I think it's not so popular because of this additional work for these solves. But say for medical applications or so, where you can know a certain machine, you can be sure that you get a certain accuracy. For other scenarios, typically with your approaches are more useful that don't that have a limited requirement for compute. Worst case, you can cut off or scale down values to apply strong damping or so. But nonetheless, for real-time scenarios, it's definitely interesting part. Yeah, so with that, I want to come to a kind of in-between summary for this chapter. So we've looked at these numerical integration schemes to basically get answers for these functions we don't yet have in an analytic form that you cannot easily compute. We can kind of make our stepping along the way to compute this trajectory. We can choose the order to get a certain accuracy, which is also typically useful for real-world applications where we at least roughly can estimate how much compute time we have, so we can choose the right algorithm for it. We typically, in all of these real-time settings, also we know where we want to start with, and then we get this evolution over time from the time integration scheme, and then we can let players or someone who interacts with the system compute and inference the simulation. So Euler step is the most accurate and really the basis of everything. Many of the other methods internally also basically do more Euler steps. The higher order methods can, as shown with these simple examples, really make big differences, need a bit more work, but really can sometimes fundamentally improve the quality and the error of the answers. And these implicit methods are great in terms of stability. They basically don't blow up if done right, but require more calculations. Right, so all of these terms that came up here, implicit, explicit, these different integrators, something you'll probably find in APIs, even if you don't implement it yourself. And with that, in a moment, I want to get back to the math spring systems, because there's also some interesting considerations, but I think we're overdue with the time for a break. So feel free to stretch your legs for a moment, and then we continue with the math spring systems in around 5. All right, let's continue. So now we can, I also hinted a few times already, but now we can really finally make our way back to the mass spring systems. I do have the notation again on a summary slide here. More for reference, I don't want to go through the details, but I hope you remember this is our basic notation. We are now dealing with position, velocity, acceleration, xva, where mass, time t, our h is still the step size, spring stiffness from Hooke's law is denoted by k here. Then we have subscripts a, I for some a position or so. Typically, the subscript I then denotes the ith point in our system. Right? We might be simulating 100 points, and then we're looking at point 10 or so. We had this big constitutive equation, basically, that put together the forces and the different terms. And if we now want to integrate this forward in time, this is pretty easy. So in the first step, right, we basically say, well, the velocity, the x derivative, that's our v, and the change of v is determined by the forces and then this additional term. So the main split is, at least mathematically, quite easy to write out. And for Euler step, also easy to implement. That's basically what we already did before, right? So I had this toy example in the beginning for mass spring systems where we did exactly that. So we said, well, we know velocity is our change of position. Let's integrate our positions with an Euler step. We have forces, maybe even a damping term. That's our acceleration. Let's change the velocity correspondingly with some step size h. So it basically, Euler step amounts to multiplying this quantity with h and adding it up, right? So this is pretty easy to do. There's a slight increased difficulty here, a slight caveat, when we're going to the higher order methods, which is why I want to bring it up. And also, what's important to keep in mind, as mentioned then, the Euler steps here, for this step, if we're treating this as one Euler step, all need to use quantities at the same point in time. So if you would be not careful in the implementation here and just override your position or so, it's important that if you want to implement an Euler step, no information from the new step should come into the picture here. So for normal Euler, this should be completely separate time, right? Time t and t plus h. Really, also please check this in your implementations, or at least mentally, they're different quantities. So it's important not to mix. What happens if we now switch to something better as discussed? Here's a higher order integrator. Let's not start with Rho 4 or so, but maybe midpoint. Midpoint now has these two steps. We go to the midpoint and then use the quantity there, as mentioned before, right? We're dealing with the same amount of information. We don't have more in a way, but we now have our midpoint scheme for the position, and we have it again for the velocity. And it's not too bad, it's not complicated, but the important thing to keep in mind here is that now these two depend on each other. So in a way, we cannot, as implemented before, think about it in terms of just saying, well, we update the position, and then there's another function that does midpoint for velocities, because the midpoint steps of both depend on each other. So in a way, you cannot separate x and v here completely, because at the midpoint, they belong together. From the notation here, you can see that by this step, now also basically requiring this second midpoint step for the position, needs a velocity at the midpoint, and the second step of the velocity actually needs the positions at the midpoint. So main recommendation here is basically don't try to think of these different derivatives, the different quantities, position, velocity, and so on, the other settings, there could be even more, and try to separate them, but think of it as something that changes over time together. So what we need to do basically is we need to take these two together, do them first, and then we need to do these. And for fourth order Runge-Kutta, you basically also would need to do, again, for all of your quantities, position and velocity, or if you have more, you do the first step, second step together, third step together, and then the fourth one, and then the final update. Right, so these steps in a way belong together, and they move your system forward together over time. You cannot easily decouple these different parts of it. Velocity and position still belong together. Yeah, so here it's on the slides. We basically have cross dependencies. For implementation, just to write it out, you need to untangle these steps of a higher order integration scheme and try to make the first step together, and then the second step, and then maybe the others. So for a mass spring system, you would basically evaluate the midpoint for position and velocity, these tilde quantities in our notation here, make this half step forward by h half. That means for the position, it's pretty easy. Just make a step with the velocity. Actually, positions are generally pretty easy for mass spring systems. But for the velocity, you actually need, as indicated here by this orange blob, you already need the accelerations, which means here we actually need to evaluate Hooke's law and all the spring connections. This really involves the whole system. This is potentially expensive. But we also need the new positions here, and then once we have these two, then we can, from the accelerations, we can compute the new v, and then with these two, we can compute, again, the new accelerations at this midpoint, and with it the final v and x values. So yeah, you can basically imagine there being a cut here between these two steps. I mean, this is just the old step, and then this is the first midpoint step, and this is the final update step. But both of them actually need A. And so now this is really potentially a very expensive part. We need to evaluate A first at our original spot and then at the midpoint again to make that update. Does it make sense? So yeah, when you implement this, it's just important not to mix and suddenly have a V from a different state in your system and use this without meaning to in one of these later steps. So for Runge-Kutta, I don't want to write it out, but again, the idea is the same. You would compute all these intermediate, these K steps that we had before on the slides, compute them all one after the other, and then finally weigh them and compute the final quantities. Yeah, actually, in this case, if you want to implement a higher order integrator, it actually also does need a bit more memory, right? So depending on your order, a bit like these state-based schemes that I mentioned before, they also do take now more states that you need to accumulate. However, the big difference to these memory-based higher order integrators is that all of these, for Runge-Kutta, you can actually throw away. These are for the current step, computed from just time t. You need them to compute t plus h, but then you can throw them all away. You don't, none of these values actually go over to the next one. This is a big difference. For the state-based ones, you really need information from the previous time step, whereas here you compute something, but you can discard it away, throw it away again. All this kind of hammering on the current time step is for a good reason. There's one really popular and also very nice recommended integrator, the so-called leapfrog integrator, from Bocksprung. So the idea is here that we have some, imagine our timeline. We have a state at time t, right? We want to get to t plus h. And now we actually imagining that the different quantities, say position and velocity, are not always at the same time, but maybe the velocity is actually stored at different locations, namely t plus 1/2 h, and here plus 3/2 and so on. And the updates then also proceed in this way by basically jumping over each other. Right, that's the leapfrogging comes from, jumping over one another. And the great thing about this leapfrog is that by this viewpoint of effectively storing the quantities position and velocity at different points in time, you get a method that with the cost of an Euler step gives you second order accuracy. So it's really as cheap as Euler. Already written out here. So for the velocity, to undo these, for the velocity, we really just do a single step by h with an acceleration. But the one thing is now the velocity actually was at half a step shifted value, and the velocity, the accelerations for that velocity are really from a different point in time, intentionally now. And the same for positions. So we're computing the position from t with a velocity of plus 1/2, just doing a normal Euler step then. But in a way, you're mixing now quantities from different times. And this really, you can show mathematically, come back to it in a moment, that this does better. And in a way, unfortunately, it's very easy to get this wrong, or to get this Euler integration right by unintentionally doing this without meaning to. So from this viewpoint that we had before, this is now basically a correct Euler integrator where we compute the forces based on some state. Then we change the positions, and then we compute the velocities based on the previously computed forces, right? Because the positions, this is what influences the forces. This is a correct Euler step. If you would turn this around and compute your forces, directly compute the velocities, and then use these new velocities to update your positions. So what I previously mentioned was wrong for Euler step. In this leapfrog picture, it's actually correct. As in the implementation, you might not have a label on your velocities that this is now stored at a different time. You might just store it as a velocity, and the positions might just be your position. The implementation, in a way, doesn't need to be aware that mathematically they are located at different points in time. Mind you, if you want to do this correctly, you would actually need to do half a step for your initialization in the very beginning to get the right velocity. But this is also easy to get right without meaning to. If everything's at standstill, right, then half a step will also just add a bit more zero, but it's the same state. So for many situations, it's trivial to satisfy this. And suddenly you have a leapfrogging method that is actually much more stable than Euler. It's really a second order method. So this I don't want to show. Again, you actually need two different quantities here. This also doesn't work for our E-function example. But for position and velocity, say my spring, this works very nicely. Please try it out in the exercise. It's really as stable as a midpoint integrator. And it, as you can see here from this mock implementation, it's really no more work than an Euler method. So you can mathematically show this, and I think it's interesting and worth a look. If we start with this shifted evaluation by half a step, the first thing is we can actually number these, equation 1 and 2. And if we now insert the equation for the velocity in the second equation, well, you just get basically these terms multiplied by h, right? That's already written down here, h times the rest. Again, h squared for the acceleration and so on. But this directly gives you basically a second order method for the positions. Right? If you look at this, you basically have h times the velocity and then h squared times the, where do we have it? The acceleration term with a factor of 1/2 here for the full Euler method. This one does drop out. Yeah, you basically just get, if you look at it up here, h times this term. So there are slight differences, but in general, this is very close to just a full Taylor expansion up to the third order terms, right? And this is what we discussed, is basically a second order method. For the velocity terms, we can look at, we can play around with this a bit. So one popular tool here is, well, we can do a Taylor expansion in all directions. So we can look at our velocity and do a step by plus h and a step by minus h, right? Taylor series in a way does not care about the sign of the step we're making. And if you write out the Taylor series, it's very similar. The only difference you get is that the uneven terms for a negative step size keep their sign, right? So if we have a squared or for any even order, then the minus sign will cancel out. But basically here the first order term and maybe a third order, if we would look at this third, fifth, and so on, would keep the minus sign. But mathematically, we can just write these two out. They're both exact in a way still, because this is standard Taylor. We have two exact equations. We can subtract one from the other. Namely, we can subtract the second one from the first, which is what's written down here. And because now all the terms are the same, apart from these uneven ones, this terms here, most of them cancel out. So what we're left with this difference is that this one will cancel out, the second order term will cancel out, and we're just left with 2 times the term of the first derivative of the velocity, the acceleration in this case. Unfortunately, the error terms here, these truncated terms that I haven't written out, those are not exactly the same, so those don't cancel out. If those would cancel out, that would be great, then we'd really have an accurate method, but we're actually keeping all of those. But because also here the second order terms that cancel out, this now really shows this is a second order method mathematically that you get with leapfrog based on the simple change of kind of reusing velocities. So this is important to keep in mind. So much for the theory about leapfrog. Please try it out. A few more comments for today. The discretization actually matters a lot. Discretization means we have something we want to simulate and we need to get it into the computer, into a discrete representation. And unfortunately for these mass spring systems, the way to do it is non-trivial. It seems like a very simple setup, but as a thought experiment, let's look at 4 points and connect them with springs. Might be very fast to compute, very simple. Let's imagine we now have a more powerful computer and we now want a fancier simulation. We want to invest more resources and do this better. Well, obviously, let's put in more mass points, but it's unfortunately for springs completely unclear how to now connect these additional points such that they give something better like the simple model before. Of course, we could go in and connect all these, but can someone imagine what the bad thing is if we just keep on doing this everywhere, right? If we connect it like this, the disadvantage. Yes. A lot of connections we don't need. I was thinking of something different actually. In terms of behavior, if you think about the first square, it's basically a single block. Yeah? You repeat the problem, yeah, right? You could imagine that if we, let me write it out. It's worth thinking about for a moment. If we now had a certain K stiffness here, right, for these springs, maybe if we would choose the different K here, we would actually get something that's pretty similar. You could imagine that there's some way of telling us if we have springs that are half as short, we need to adapt the k by square root 2 or something. Right? It doesn't exist, but could be. So even in the setup, maybe we could find something that works quite similarly. The problem is that I wanted to get to, if we just connect it this way, this system can completely fold over. At this midpoint, there are no connections between these two halves. So this, on the right here, you can fold into about half the size, and you have no forces. In 3D, it would be easy. In 2D, you could be unlucky, and it could be pushed over or so, right? But if these points are exactly down here again, the springs have exactly the rest lengths, no forces, this is a stable state. This is something the left version cannot do at all. If you try to do this on the other side, right, you're compressing the springs all the way, you get a huge force. So this is an indicator that there are actually fundamental changes here. And right, I don't want to go into detail, but mathematically, there are no equations to tell you how to change the springs, and it's in general actually not clear how to add more springs. I mean, the problem I just mentioned you could fix by adding maybe the original ones again, like the green ones here, right? But yeah, there's no clear algorithm telling you that what you would do here is really something better than on the other side. There are different mathematical formulations that do have this property, that do converge to a single clear answer as you add more resources. But for mass spring systems, that's actually difficult, or impossible, I should say. Difficult sounds it's actually wrong. It's really, at least so far, we don't have any algorithm to really transfer and refine mass spring systems. But this is also something we get back to. They're nonetheless a nice starting point if you want to start with numerical simulations. And in a way, they're also really a classic case. So I want to show one example here. It's a bit of a story, but I think one worth mentioning. So by now, 18 years ago at CMU, Carnegie Mellon in the US, they had basically also hackathons, what they called experimental gameplay project, where you had a week to create a game. And there was a certain theme. I think this was only allowed for single persons, but basically was a competition. And someone came up with a game where you needed to basically connect a lot of small different blobs and basically just build a mass spring system. So you had these blobs falling from the sky, and then you're supposed to link these up with springs, and the springs would just connect. And from that, you're supposed to build a tower. This was coded in basically a week. It is really a simple mass spring system. But turns out people actually like this. So this was, I think, available on the web, and people played it a lot because, right, as you can imagine, you add more and more springs and things become heavier and becomes unstable. And this, I have a video in a moment, does wiggle around from the springs. And here on the right, you can already see some high scores. So this is a pretty large tower. This takes quite some work to build manually from all these points. But yeah, it's basically a small game built around a mass spring system. And this became very popular. So this, because this demo was so successful, they turned this into a company, and then also was back then a bit of a novelty that was developed with open source, with a lot of communication, keeping the players involved and making it very transparent. And this turned into this World of Goo game. Has anyone played this, World of Goo? Some, okay, I can recommend it. It's actually, by now it's old, but it's fun. It's an interesting game. And then also went on to win a lot of awards. But in a way, it's really just that. It's a fairly simple two-dimensional mass spring system turned into a very nice game around it. And this is worth showing in action. I happen to have a gameplay video here. Yes. So you can see the mass points. They're, in this case, they do have a life, but interestingly, they don't have a mass before you place them. the springs get connected automatically, but you can already see here a bit, this is wobbling around a bit. This is really just that is a small mass spring system. And then what I guess the game did really well is to very gradually keep it interesting and make it more complicated. So the game introduces all kinds of different of these blobs and different connections and different extensions of the main gameplay elements. So this level just now that you saw was sticking to the original goal of this demo to just go higher. But this is already slightly more interesting. Now you have to actually make a bridge basically. And I think this one doesn't have failure cases now, unfortunately, but you can imagine if you do this wrong, then the springs at some point also break if they stretch too much, and then the whole thing breaks down. But this is a correct answer, and triangles are actually pretty good primitive to build from. And here you can reach the exit for the mass points. Let's check the next level real quick, but in a way, I think this is a good example of this concept that I mentioned in the very beginning, that gameplay is a good basis for many games. Here it's also a kind of classic example that the whole game is about exploring the physics of a mass spring system, and this is where all the gameplay comes from. So I think by now this is probably very easily accessible, and I can recommend trying this out, even if just to see how it breaks. Okay, so there's now a slight variation where you first have to pick up these the blobs, the goo pieces, by building the connection down, and then you can actually build it up. And it definitely is fun to. Okay, yeah, sorry. And fortunately, in this demo, okay, now it does break a bit. Now it does fall over. And that's actually behavior you probably will also see in your own exercise. These springs can fold and then collapse. And yeah, no, definitely giving a lot of interesting behavior. So, recommendation if you want to see mass spring systems in action in real-world applications. I do have a few comments here about this larger topic. The core of this whole chapter was numerical integration. So mass spring systems are a very good way to try this out, because there the integrator you choose matters. It's something you can try in the exercises. It really makes a difference whether you have explicit Euler or explicit midpoint. You will see differences in your simulation. But this whole topic of numerical integrating, basically computing an integral of some quantity, here it's a real position, but this comes up in other situations, is a very broad one. It's good to know what these methods, they do repeat a lot. For mass spring systems specifically, it's actually the situation where it doesn't make too much sense to use Euler's method. The exercise, please nonetheless try to code a accurate Euler scheme before you go for leapfrog, but you'll see a difference. And mass spring systems also do come with a whole class of challenges, from inversions and changing mass points. That is also something you can actually try out in this fourth project phase of the exercise quite nicely. Yeah, but these integrators are really a broad topic. I do have a few recommendations here for implementing these schemes, also maybe a bit even more relevant for rigid bodies in a moment, but it's very tempting to, when you try this out, say, oh yeah, okay, I followed the slides, I've written this down, it's all there. It seems to work for a small example. Let's start playing with larger ones. That's something I really cannot recommend for these numerical schemes. So we're trying to force you a bit to not do this with the exercises by basically having you calculate these things on paper first. But looking ahead, if you ever need to deal with this, I can highly recommend to not directly go large in such a simulator. In certain other systems, it might make sense if you have a UI framework or an interface design or so, you might be able to write a lot of code before you really start testing it out, and you might be then able to go in and test different parts of it separately. For these numerical simulations, I can really recommend to make it as simple as possible in the beginning and make sure you get the answer you need. It sounds very obvious, but it's easy to forget in the heat of the moment. If you think, oh yeah, I'm sure it's working, let's go large and try something. It seems more fun at first if you can directly try a big example, but it's typically quite difficult to go back in. Or what happens in 99% of the cases, if you start playing with complex things, you need to go back anyway and figure out the basics again. You need to maybe go back to a piece of paper and calculate and double check that your steps of 1 or 2 points did give the right answer, because from a large example you will not see what the error is that easily. It will just explode in some point, or get stuck or give an error. So even if it seems like more fun to directly experiment with it, it's actually typically much less frustrating and more fun if you build this up slowly and make sure the different steps work as they should. You probably need to go back nonetheless, even if you do this, because it's easy to overlook. And with the simulations, +1, -1 error at some situations might look pretty good for most of the simple cases, and suddenly when you try something more complex, it still goes wrong. This might be difficult to track down, but I can really recommend to try as much as possible to build it from small examples that you verify to larger ones. Because yeah, in the end, that actually should be more fun to work with it. Yeah, on the slides, right, there's also a summary about the whole chapter, and then next week we can start with the rigid body simulations as a very, very different, right, different beast of simulators with different challenges. Are there additional questions at this point? We had a few discussions, or time for lunch. All right, then thanks so far. See you next week.